Robin loves hiking, canoeing, camping, and is often staring at rocks on the ground instead of the scenery around her. Her work allows her to combine a love of nature with a curious mind. She got a master's degree at the University of Wyoming, also in geology and geophysics, where she studies the uplift history of the high Andes Mountains. Robin is a graduate student here at Yale, back on Earth, in the Department of Geology and Geophysics at Yale. She focuses, or rather uses, a technique called clump isotope paleothermometry to estimate past temperatures during greenhouse climates at a time when there was little to no ice on Earth's poles. Outside lab, her dream is to encourage other young scientists, those who have ever collected seashells or made baking soda volcanoes, to get even more excited about the natural and physical sciences. Today, she will guide us on a tour through time of Earth's vast and rich history in science and its origins. Please help me welcome Robin.
Hi everybody, I'm Robin. I am a geochemist and I study paleoclimates. So that means I look at the chemical signature of rocks and fossils and try to better understand the Earth's climate through its long history. So before we delve into the rock record though and try to understand the mysteries of our past Earth, I want us to take a moment to just visit our current Earth. This is an image of Hurricane Joaquin that hit on October 2nd of this year. And as you can see, it's taken from the International Space Station. And as you can see, this is familiar. There's cities in the distance. We live in these cities. There's the storm forming off the Atlantic Ocean that we all know here in New Haven, right out our front door. The continents at this time, we know this map. We see it in our history books and our geographic books. And there's ice at the poles, like Zach was saying. Now, the Earth of the past looked very different, and looked very different at different time periods. Very different from what it looks like today. What did the Earth look like in its humble beginnings? Well, not that different from a bunch of other rocks zooming around the solar system at the time. Two of those such rocks, the proto-Earth and the proto-Moon, collided violently 4.5 billion years ago, producing a mass that spewed out, and gravity did the work after this violent collision of selling all the densest material to the Earth's core. The least dense became the Earth's crust, and all of that material that was ejected out from this collision consolidated in orbit around the Earth and became the Moon. Now, we can get an age of this collision, but unfortunately not from any rock material on Earth. Due to the conveyor belt motions of the Earth's crust, tectonic plates override each other and then sink below each other, so a lot of Earth's oldest crust, the record of that is erased. So how do we actually know the age of this collision? We study lunar rocks. One of the ways we can do that is using a tool called radiometric dating. Now, when rocks or minerals crystallize, they basically set their chemical signature, except for radioactive elements. Radioactive elements like uranium decay at a known rate to lead, and thus we can look at, say, this moon rock from the Apollo missions, which is rich in uranium, and look at the ratio of uranium to lead to estimate its age. So based on uranium-lead dating of lunar rocks, we know that the Earth-Moon impact, and thus the formation of the Earth, was 4.5 billion years. Now that is a big number to kind of grapple with and picture. So to help demonstrate that, I would like to ask for 2 volunteers from the audience to come up here and help me, if you would. People want to raise their hands? Yeah, come on up. Another volunteer? Yeah, come on up. So I will ask you to stand over here. If you can take this end. If you want to come here and grab this purple end. And take this and just walk that way. Watch where you're going now. Keep going, keep going. So this is a scarf that a student knit for me, actually. But the length of this scarf represents 4.5 billion years, total length. So we have the Earth-Moon impact right here at this end, this fringe. And all the way down here, on this ribbon, we have, almost by the purple fringe on the other end, the evolution of humans. So that's a lot of time. This is what geologists call deep time. It's a lot. And for those of us who, like myself, were obsessed with dinosaurs as a kid, this ribbon right here is the evolution of the first dinosaurs. It's not really a lot of time between those two when you look at the whole history of the Earth. And if you keep going all the way back in time, somewhere around here, you have the oldest fossils ever, the oldest evidence of life. So there's a lot of time in between and a lot of interesting periods in which Earth looked very different. So thank you, ladies, for helping out. We can just wrap this back up. So, to go back to Earth's early beginnings, right before, right when we had the first signs of life, this is what Earth would have looked like. The Earth was 30% less bright than it is, or the sun, sorry, was 30% less bright than it is today, suggesting it would have been a lot colder. But the rock record shows evidence of marine sediments, suggesting that there was liquid water then. Now, scientists think this is due to much higher concentrations of greenhouse gases, which makes sense because Earth's internal engine was churning much more back then, so we would have had a lot of volcanism, which is why there's volcanoes back here in the distance. Now, those marine sediments from this ancient time period show evidence of reduced forms of iron and sulfur, suggesting that there was little to no oxygen on the planet. So you and I would have not survived. This would not have been a happy place for us to live in. And in fact, most of the critters had some other way of making their living back then. That is until about 3.5 billion years ago, when the first photosynthetic organisms evolved. These guys, blue-green algae or cyanobacteria, lived in these mats, which you can see here, called stromatolites. And the evidence for them spewing out oxygen, basically as a waste product of photosynthesis, comes in what we call banded iron formations. This qualitative evidence of the oxygenation of Earth's atmosphere shows dark bands of anoxic iron, reduced iron, and oxic bands of red iron, showing how this slow process of oxygenating Earth's atmosphere was happening. So, unfortunately, oxygen poisoned everything back then, but it was great for us, right? And everything that came before it, after it, dinosaurs included. Now, this qualitative evidence of the rock record is commonly used by paleoclimatologists. Another example is a drop stone here, this angular boulder that fell in really finely laminated beds of marine sediments, as well as this poorly sorted glacial till here. These are both geological rocks that are produced by glaciers and were found in low latitudes about 600 million years ago, suggesting that glaciers from the poles move all the way to the tropics during this time period. This has become a period well known by geologists and earth scientists as Snowball Earth. And that's pictured here in a cartoon. You can see this process is started by what we call a positive feedback loop. So you have ice form at the high poles. It's bright, it's light colored, it reflects solar radiation, which cools the Earth, which builds more ice, and so on and so forth, until you have a sort of runaway ice house. So how do we get out of this? If we're a giant snowball, why are we here? Why is life here? Well, the Earth is still churning. The inside's molten rock is still moving around, and eventually volcanoes kick in, spew out a bunch of dust and soot and CO2, a greenhouse gas, and that soot covers the ice, making it darker, allowing more radiation to absorb on the surface, and melts the ice, and you have that positive feedback loop going in the opposite direction. CO2 as well as a greenhouse gas warms the atmosphere. So that is how we got out of it. Now, Paleoclimatologists like myself can also use quantitative tools such as stable isotope geochemistry in addition to the rock record to better understand past climates. One of those tools that we use is stable isotopes. These, unlike the radiogenic isotopes, uranium and lead, that we use for dating, they do not decay. They simply differ on their mass. So for example, oxygen has isotopes, stable isotopes. So oxygen in seawater can either have the common oxygen-16 with 8 protons and 8 neutrons, or it can have the rarer version flavor of oxygen with 8 protons and 10 neutrons, oxygen-18, those spinning cartoons up here. So they simply differ on mass, and because it is easier to evaporate a lighter isotope than a heavier isotope, water vapor, precipitation, and snow is more abundant in oxygen-16 than the seawater from which it evaporated. So during cold time periods depicted down here, ice traps more 16O on the continent, and so seawater during cold time periods is heavier, meaning it has more oxygen-18 than in seawater in warmer climates. So we can use this phenomena and look at fossils, including these cute little critters, benthic foraminifera here, which are these tiny single-celled organisms that live in the deep ocean. And because they grow their shells in seawater, they incorporate oxygen from that seawater into their calcium carbonate shells. We can grind them up, dissolve them, basically destroy them, and get a record of temperature. Because the ratio of 18O to 16O is temperature dependent, we can develop things called oxygen isotope temperature curves, like this one here. This is for the time period, the late Cretaceous, when dinosaurs are roaming the planet. And as you can see, at the peak of warming, based on oxygen isotopes, the global mean annual temperatures were 10 to 18 degrees C warmer than they are today. Today is about 14. So what did it look like, actually, 10 to 18 degrees C warmer than it is today? Very different. You can kind of see continent outlines that look like today, but what's striking, especially for those of us in the US, is that there's a shallow tropical intercontinental seaway that stretches from the Arctic to the Gulf. This is because there's no ice at the poles and sea level is much higher. In addition, because it was so much warmer, the tropical belt was expanded. We actually have alligator fossils in Alaska. They don't do so well today. So this is what we call a greenhouse climate. The levels of greenhouse gases are much higher during the late Cretaceous. Another example of a greenhouse climate is what we call the Eocene, about 50 million years ago. So after the age of the dinosaurs, this is when mammals are evolving. Looks more like today, except we don't have the Himalayan mountains yet. The Isthmus of Panama has not formed, and we still have no ice at the poles. We think, based on other geochemical proxies that suggest levels of CO2, that they were around 500 to 1,500 parts per million. That is compared to the pre-industrial levels of CO2 before the Industrial Revolution, around 280 parts per million CO2. So because of those higher levels of greenhouse gases, the planet was much warmer. It was a lush tropical world, might have looked something like this, where mammals were evolving. These are actually early horse ancestors that were about the size of dogs that lived back then. These are fascinating time periods that we all study. It's great to study paleoclimates just because they're really interesting and totally different from the way the world looks today. But one of the other important reasons scientists are interested in studying paleoclimates is because by studying the past and how the Earth reacted to increased greenhouse gases, we can better understand how the Earth will react in the future to human emissions of CO2. Now, this past year, we have hit at a landmark level of around 400 parts per million CO2 compared to that 280 pre-industrial level. And here are some projections of Earth's temperature change compared to today for the future, 2050, 2100. Now that level of 400 parts per million hasn't been that high since the Paleocene, around 4 million years ago, when the Earth's average temperatures were 2 to 4 degrees C warmer than today. Another time period that's commonly studied by paleoclimatologists is the Paleocene Geocene thermal maximum. You can see here a rapid warming event. That rapid warming, the increase of greenhouse gases at that time that caused it, is around the scale that is happening now due to humans. So what's really important, not just for curiosity reasons, although that is what got me into it initially, was finding fossils on camping trips and going to museums, is that we can use the past of Earth's climate to better inform policy and make plans so that our society is prepared for when the world we know of today becomes the Earth of tomorrow. So with that, I'll take any questions.